No, okay. Let us start today's lecture. So I'm going to talk about different things about functions. So first goes how does differentiation look when we have the tools of non-standard analysis. Suppose we have f of x in continuous function, say in 0, 1 or in the whole line, it does not matter. And take x, no, say internal point. Yes, and we can consider its first of all corresponding non-standard interval star 0, 1. Now it contains all bounded non-standard real numbers which are positive or non-negative and less or equal than 1. Nothing unusual. And consider star f. Star f is non-standard, say, extension of the function f. So it's a function from star 0, 1 to star r. Yeah? And it is continuous. It is continuous in the sense, so f is, it is called S continuous. At the point x0, if for any point x which is infinitesimally close to x0, s star of x is infinitesimally close to f star of x0. Yeah. So infinitesimal changes of argument correspond to infinitesimal changes in the function. We already discussed it last time, and I give a definition. F is let's call it S differentiable at x0 if there exists bound let me write standard R, so just a real number such that f x plus epsilon minus fx equals a epsilon plus h of x epsilon or any epsilon which is infinitesimal, and this is remain the term h h of x epsilon divided by epsilon is infinitesimal for all infinitesimal epsilon. So the incremental function when you go from x to x plus epsilon is linear function plus some remainder which is of higher order. This is the substitute of usual definition of differentiability when instead of being infinitesimally small we say something goes to 0 and all other without changes. Now, for example, consider fx equals x squared, and then we write fx plus epsilon minus fx equals x squared plus 2 epsilon x plus epsilon squared minus x squared equals 2 epsilon x. Let me write 2x times epsilon plus epsilon squared. So this is h of x epsilon, and this is a, yes, and h of x epsilon divided by epsilon equals epsilon squared divided by epsilon equals epsilon, which is, of course, infinitesimally small if epsilon is infinitesimally small. So, no, this was example considered in the same way by Leibniz. So, we have the same result. Next function is differentiable on this segment if it is differentiable at every point, and all the usual rules of differentiation. Now let me consider again the Leibniz rule, how to differentiate the product of two functions. So consider f of x times g of x. This function equal, say, k of x. So k of x plus epsilon minus k of x equals f x plus epsilon g x plus epsilon minus fx gx. Yes? And now let us make the usual trick equals f x plus epsilon g of x minus f x plus epsilon g x plus epsilon plus f x plus epsilon g x plus epsilon G x minus fx gx. Equal f.
So is it minus or?
Excuse me?
I think this is a minus. Last one, last line.
No.
Because otherwise this is not.
Minus plus no. Fx plus epsilon
Plus the
g. Just a minute. Of x plus epsilon
minus
f
x plus epsilon
x plus epsilon
g of x.
gx, yes, equals f x plus epsilon g x plus epsilon minus gx plus gx f x plus epsilon minus fx. Now let me represent fx plus epsilon. Fx plus epsilon. Let me write f prime of x plus h f of x times epsilon g prime of x epsilon plus plus h g of x right, x epsilon plus g of x times f prime of x epsilon plus h f of x epsilon. Equals fx g prime x epsilon and g prime of x epsilon. Let me write first principal term plus g x f prime of x epsilon plus all other terms plus fx h g of x epsilon it is plus epsilon square this time there f prime of x g prime of x plus epsilon f prime of x h g of x plus h f of x epsilon times g prime of x epsilon plus hf of x epsilon h g of x epsilon, and here plus g x hf of x epsilon. No, okay, so the first two terms are the principal terms, and every term after this, if you divide it by epsilon, it will be infinitesimal by this or that reason. For example, this is infinitesimal because this is finite, and this is divided by epsilon, this is infinitesimal, and these are two finite, and this epsilon squared divided by epsilon will be epsilon, and so on. Yes, equals f x g prime of x plus g x f prime of x epsilon plus hk of x, where hk of x epsilon x epsilon is infinitesimal, and if you divide this by epsilon, here is this factor epsilon, then we have this k of x plus epsilon minus kx equals let's see. This is the Leibniz rule, of course. So we go step by step, like in the familiar proofs in elementary analysis. But here, instead of considering different epsilons or deltas, or talk that something, some functions go to zero, we use this convenient thing, infinitesimals. No, all other property, no, for example, chain rule, it is also proved this way, more or less straightforward. So, you see, it is convenient, and this somehow, I would say, confirms the infinitesimal viewpoint of Leibniz, who thought exactly this way, and our familiar reasoning with epsilons and deltas was introduced first by Cauchy, and then even more by Weierstrass, so it was rather late in that. Okay, so this can be generalized to maps of, say, domains in Euclidean space, yes, to maps of domains in infinite dimensional linear space, and so on. It goes all the same way. Now it is more interesting the next operation, which is integration. So given a continuous function, again fx, say 0, 1, now you understand that it can be replaced by other domains in space of different dimensions. So it is just to be concrete. What is integral from 0 to 1 fx dx? Okay, so let us start familiar process. Let us take our segment 0, 1, and let us define partition of this segment by the point x0, x1, and this is xn. Yeah? Now let us choose a point inside each of these segments. It is x0 prime, x1 prime, x and minus 1 prime. Yeah? And let us write the Riemann sum. Let me write S depends on F, and it depends, let me write it, of N, depends on epsilon. I say in a minute what it is. Depends on x0, xn, x0 prime, xn minus 1 equals sum x k plus 1 minus xk f xk prime, k from 0 to n minus 1. This is a function. Now f is a sort of parameter. It depends on all these things. So how does it, what it is? N is the number of the points, no, n plus 1 in fact, number of the segments of partition. And epsilon is enters a condition for domain of this function. So the domain is defined by the following conditions. Dom of SF, set of x0, xn, x0 prime, xn minus 1 prime, such that x0 equals 0, less than x1, less than xn. Let me write both. Less than x0 prime, less than x1, less than x1 prime, and so on, less than xn minus 1, less than xn minus 1 prime, less than xn, which is 1. And xk plus 1 minus xk less than epsilon for all k. So we have this. So epsilon defines how close are the points of partition to one another. We are interested, of course, in small epsilon. No, simply because without this condition, we can say concentrate all the points in some part of this segment, and it will be wrong. So let me call this condition 1. This domain of our SF. And n is, okay, n n and epsilon positive. This is a complete description of domain of this function. And now let us extend the function f and extend this function sf into non-standard mode. Yeah? So consider the function star sf. So star SF, we have to be here a little more careful. Here we have a finite sequence of points. Yes? So when we go to extended model, then this sequence may be infinite. So we consider SF is the following n epsilon in R plus, and we have sequence X from the set 0 n. So this notation means all the integer numbers between 0 and n, including 0 and n. Yes? To R. Yeah? So this is a function from some initial segment of natural numbers into real number. And x prime is from 0 n minus 1 again to R. And then you have this condition 1. Which is written here. So this is domain of our function, and this is a set. All the elements here, all these objects are sets. Yes, and so we can consider star SF. Consider this function. It is a function defined on star. Yes, we have to start this domain. Domain of star SF. So n is in star n, epsilon in star R plus, so it can be infinitesimal. X 0 n to star r, it can be finite or infinite, depending on n. And x prime 0 n minus 1 to star r. And the function SF, it is the integral sum, is also continued on all this domain. Yes, and condition plus condition, I would say, star 1. This condition 1, condition 1 says exactly these things, and condition star 1 says is written and says exactly the same. Yeah. So the points 0 and all these points are in one-to-one correspondence with numbers in this segment. But the value of this function we define by transferring from the function SF. So we don't need to compute it again. If you know it for any finite partition, then we have the value for infinite partition. If you take epsilon, infinitesimally small. It's clear? So what we did and what was intuitively thought by Leibniz is that we partitioned our segment into infinitesimally small parts. For each of these parts we found sort of the area of corresponding triangle and then took the sum. We can, I would say, descend to our model, consider the functions index set I, where the ultrafilter is defined. And so for each I, we have some finite partition and correspondingly some function SF. Yes, and then the size of this partition, namely epsilon, which depends on I, goes to 0 when you go further along this ultrafilter. And we have some number. So what can you say about this result? It turns out that in this, under these conditions, the result in fact does not depend on the non-standard model, does not depend on ultrafilter and on infinitesimal epsilon. Yes, here is one more condition, that n times epsilon more than 1, otherwise it would be impossible. So the distance is less than epsilon, yes, but the sum of these distances is 1. The number of segments is epsilon, is n, so n times epsilon should be more than 1. Yes, so it turns out that result does not depend on details of the model, fortunately. And what we get is our usual integral. Why are you so sad? No. No, it is Okay, so how is this proved? So the steps. First, f is continuous. Continuous in our usual sense. This means that model fx less than some n. So the function is bounded. If model fx is less than n, then integral sum is also less than n. Yeah, so SF less than n for any partition. Yes? No, if SF less than n, then by transfer we get that SF less than n. In fact, I forgot to say that if you take this star SF, yes, it is a non-standard number. It is bounded, so we have to take its standard part. So a definition of integral from 0, 1 f dx is by definition standard part of star SF for infinite n and infinitesimal x. Yes. So first of all, we have star SF. This means that a standard part of star SF is also bounded by the same n, by transfer principle. So we have the one thing. Now the second thing, we have to compare the results for different partitions. Again, following the usual proof of convergence of integral. So suppose we have the following thing. X1 xn x1 prime xn minus 1 prime and x0 and say z0 zm z0 prime zm minus 1 prime are two partitions. Yeah. They can have different number of segments. No, we can consider a partition which is obtained by union of this partition. Partition T0 T m plus n, which is the union of two previous And what is epsilon here? Take epsilon equals minimum, say epsilon n, epsilon m. Well, here is epsilon n, here is epsilon m. P equals n plus m is the number of points in this partition, and let us and T0 prime T n plus m minus 1 prime new intermediate point. Now here we have to use the fact now that the function is f is uniformly continuous. F uniformly continuous. This means that x 1 x2 fx1 f of x2 looks like a repetition of the continuity, but if you look closely, it is different. So the function is uniformly continuous, and this means the following thing. If you estimate the change, so S of say n epsilon n x1 xn minus 1 prime minus S n plus m epsilon n plus m c1 c n plus m minus 1 prime. If you continue this, and if I assume that x that n is infinite and n plus m is infinite, and epsilon n and epsilon n plus m are infinitesimal, then after all we'll see that this is infinitesimal. No, this means that result does not depend on these parameters, points of partition, simply because we after that we take standard part, and standard part erases these infinitesimally small terms. No, you know what? We can do it more details, but frankly, I have little time for this, and maybe it's better to do it in the problems. And first and second, that it step by step repeats the proof in real analysis. For the definition of Riemann integral. So there also we consider two partitions, consider the union of this set of points, and estimate what is the difference, what is the oscillation of the function on some small intervals, and the result is the same. So why did I tell all this? Because this is the simplest, the first and simplest instance of integral, which of course can be defined in different ways. But we can think about less obvious situation or less classical situations. For example, we can follow this way in finite dimensional domains, but what about infinite dimensional domains? Yes, what about, say, what is called Feynman Integral? Yes, it is also tempting to attack this thing, try to define rigorously what is Feynman Integral using non-standard tools. And I know that some work in this direction is being done, but without much success. So it is still open thing. But this non-standard approach can be useful here. So it is a really topic of thinking. Okay, now I wanted, what time is it? 5. Okay. Okay. So I want to go to more non-standard, proper non-standard situations, possibly more interesting. Which is called internal functions. So what is internal functions? Let us start from the following set, F. Is the set all functions from R to R. And consider, what can we say? That F is element of our universe U. We can even estimate at which floor is this set. So each function is given by its graph. Yes, graph is subset in the set R by R. So each this is in the floor number 4, as we found already. Now this subset R by R is in the floor number 4. Subsets in this R in the floor number 5. Yes, and the set of necessary subsets is at the floor number 6, so it lives on the 6th floor, if you wish. So it is an object entity in our universe, in the standard universe. And so consider the element star F in star U. What is it? It is the set of, it is, F is element of in U6. So what is the definition of star F, which is in star U? F in star F, if F of I, yes, and for each I, F of I, elements of F for almost all I. Yeah? No, if the function is not everywhere defined, then no, okay, its function enters there together with its domain of definition. So f of I, so for any I we have some function, yes, and so what is the yes, this is some function. Now, how can you, I would say, recover the function itself? So the function should be a map from somewhere to somewhere. Yes, if the function of f is a function, say, from some set in R into R, yes, then it would be natural that the function in f star is a map from some set in star R into star R. No, we can, of course, recover this. Consider a set, so what is domain of f? It is the set of, say, x of I, such in domain of f of I for almost all I. Yeah, so this is domain of f. So x of I, it is a sequence of our f, and by definition, this point, no, in fact, equivalence class of these points, modular sets of measure 0, is an element of star R. Yeah, it's element of star R. So it is all in star R. Domain of f. Now the value of f. So if x in domain of f, then what is f of x? F of xi also almost everywhere. So if you have this sequence x of I, and this x of I for almost all I is in domain of f, so we can find value of the function f at this point, f of I, yes, and have a sequence f of xi, which gives us the value of the function. Yeah? So this function of this form is called internal function. It corresponds to the general definition of internal object or internal set. It is the set such that this set itself is element of our non-standard universe. here this function is a set. Yes, so why it is a set? So f consider set x in f and f of x, yeah, graph of this function, and the set of these points. This is a set of pairs, so it is a set. Yes, and this set is we can simply identify the set with f. So this way we construct a function. Now construct a function. Now we started from the set of all functions, and then this set of all functions is object of our standard universe, and we consider its non-standard counterpart. Again, elements of this non-standard counterpart are internal functions. So f internal function. No, it is maybe too general and too abstract. We can consider more concrete situation. If you have f of x and say a, is some f, a is a parameter. No, it can be a number, it can be a set, something like this. So the function with parameter. And now let us take this function and take star f. Star f is defined for x, xa, here x in star r. A is no, if a is also a real number, also in star r. So it makes possible to make a say infinite or infinitesimally small. Yeah. No. So consider examples of such construction. So this star f of x a for a is non-standard, say infinitesimal or infinitely large, is example of a internal function. Yeah. So consider example f xn equal sine nx. X in R n in n. So this function, no, just the usual function. And now let us take star f xn for n infinity. Star n minus n. Say this. So what is this? this is graph of this function for finite n. When n goes to infinity, it becomes denser and denser. And for n infinite, in our usual scale, finite scale, we see infinitesimally dense waves. Yes, with infinitesimally small wavelength. No, okay, I have something more to say about this example, but consider different example. F x n example equals, okay, 2 over pi arctangents and x. Now again, why 2 over pi? To make it plus or minus 1 asymptotically. So it is a function like this, but when n goes to infinity, it becomes steeper. It is something like this. Yeah? And we are again interested in the case when n is infinite. What is it then? And the next example is, say, the Gaussian function. Fx equals square of epsilon of 1 over 2 pi epsilon e minus x square over epsilon. No, this fx epsilon. This factor is to make integral equal 1. It's normalizing factor. So what is this? No, for finite epsilon, it looks like this. So this height is square root 1, 2 pi epsilon. So when epsilon goes to 0, it is this height goes to infinity and this width goes to 0. But it's interesting when epsilon is infinitesimally small. What can be said about this function? Yeah. So these all three functions now have something in common that no, we can feel something mysterious in these functions. And unfortunately, I have no time today. What time is it?
20.
Huh?
25.
25, okay, I have to finish. So I will continue next time because it can be said much more about these functions. But let me finish with example of a function which is not internal function. So these functions are internal. They are exotic but internal. So which function is not internal? How do you think? No, we know examples of the sets which are not internal. Yeah? So let us consider characteristic function of of external set. So function f of x equals, say, 1 x 0 and 0 otherwise. No, simply if it were internal, then the level set of internal function is internal set. Yeah? And for this function, the level set is the set, say, where f is 1, is a set of infinitesimal numbers. And this set we know is not internal. So this is example of external functions. Next time I will show that the world of internal functions is very wide. For example, all the distributions can be effectively realized as internal functions. And these functions are not only internal, they are, in their internal sense, they are smooth. Yeah? So, in the world of non-standard functions, even internal functions, we don't need very terrible discontinuous and so on functions. More or less every function there is infinitely smooth. Yeah, so it is quite interesting situation. No, okay, so today I will finish and continue next time.